Right, so these are the notes for the first lesson from the textbook in Math 10. And unlike the last few review lessons, this is not an algebraic lesson at all. It's about understanding visually how you can show change on a graph. And eventually we'll come back to equations. So as it says here, a relation, and keep in mind anytime you see a term in bold, those are terms you need to be aware of. And on a test or some sort of assessment, you can't ask me what those words mean. So anytime you see a term in bold, keep in mind those are terms, vocabulary we should be aware of. So a relation is a comparison between two or more different variables. Graphs are useful ways to easily visualize different relations where the x-axis and the y-axis represent different variables. And so keep in mind, by convention, the x-axis and the y-axis, the x-axis is always, let's make sure my pen works. There we go. The x-axis is always the horizontal axis, the y-axis is the vertical axis. Now we don't always have to call them x and y, but if we are using those parameters, x and y, x is by convention always horizontal, and y is the vertical axis. In this case though, I want to visualize not x and y, but height and time. And so again, height and time are on the x and y axes. And it matters where we show these things. Time really needs to go on the x-axis, and I'll talk more about that later. But first, what's the scenario here? A basketball player throws the ball towards the net from the free throw line. The ball does not reach the net, so the throw is short. So first I want to visualize that. Someone trying to take a basketball free throw, and it does not only does it not go in the net, it's just short of it. So we want to visualize what the graph of that scenario, if we're looking at the two variables, time and height. How does the height of the basketball change over time from the moment the free throw starts? And so first I want to show some incorrect answers. One incorrect answer could be something like this. And the reason that's wrong is that that would imply that the ball is starting on the ground. When the height is 0, time is 0. And that would make sense if we were kicking the ball, but we're not. So that's not right. Another one could be wrong if we do something like, how about like this. Would be also like kicking it, but also waiting a few seconds before you kick it, because at this first little region here, it's on the ground. So if it's a basketball free throw, which means at the start the ball is not on the ground, it's roughly in someone's arms. And again, I'm not worried about any details here beyond just the general shape. So I don't know, I'll say it starts here. Notice I'm not labeling the x and y axes, I'm not putting any values on it. The key is it's not at 0, and then when they throw it, it goes up, but it doesn't reach the net, so it keeps going down and eventually hits the ground. Now that's it. You could then say it bounces after that, but that's it. This is what I have here is all I really need. All right, and the key is the sort of general shape of it, and that it goes up and then goes back down. It should not start, for example, that's a key characteristic. It should not start at the bottom, but it should end at the bottom because it misses the net. And so it's, other than that, the curve is uninterrupted. There should be no sort of changes to it. All right, let's go to the next scenario. This time I'm still showing height and time. This time a basketball player throws the ball towards the net from the free throw line. The ball hits the backboard and goes into the net. So like before, I want to start with a mistake. So this time it hits the backboard and then goes into the net. So if you visualize something like this, I'm actually going to draw a little basketball net here. My amazing artistic talents. There we go. So this here, I'm coloring in, that's the backboard. So if you visualize something like this, where it goes in, hits the backboard, and then bounces through and goes down, you're visualizing it correctly, but you're not drawing the graph correctly. So if you look at what I drew in green here, this means, at first it's okay. At the start, when time is 0, the height is some point above the ground. It goes up when the person throws it. It hits, but then here's the problem. After that, it starts to travel back in time. And that's what this is really showing. This is showing the same object now reversing in time and then going back down. And so this means at some instant, let's say right here, at that point in time, whatever that is, the ball exists at two different places at the same time. Now, you might see that in a movie, but that will not take place in real life, and so at least not at this time. And so that's what that's showing. And so, again, I'm not trying to show the trajectory. What I've drawn in green is the trajectory of the ball. I'm trying to show how its height changes over time. So how do I make this correct? Well, it starts the same way. Starts right here somewhere, goes up, and then, I don't know, let's say right here. This is where it hits. I'll put a little dot. This is where it hits the backboard. After this point, yes, it bounces backwards, but the height, again, this is time here. The height, you may go up a bit, may go down a bit, but time is always moving in this direction. And so let's say it bounces up and then makes its way into the net. Then it would still go up because it's still going forwards in time. And let's say right here, it's going in the net. And let's say it hits around a bit, so maybe, I don't know, there's some sort of change, and then it goes back down. So something like this. The key is that it never goes back on itself. And that, unlike the last graph, this region here is not a perfectly smooth curve because it hits, and at some point, you know, the height is changing, whether it's actually bouncing up or in some way, but it can't go back on itself. And so something like this is correct. And again, if I want, I could show it bouncing or whatever, but we don't really know what's happening after that. You know, maybe someone catches it, so we'll just leave it at that. I guess it's a free throw, so someone's not going to catch it. Anyways, last one. Same scenario. At first, basketball player throws a ball towards the net from the free throw line. This time the ball hits the backboard and bounces back towards the player. So again, I'll just start with a mistake. Maybe I'll draw the backboard in gray here. So here's the backboard. Here's the net. Very big net. All right. So if you visualize something like this, where it bounces and then goes back towards the player, something like that, let's say. Again, that's the trajectory, we say, but that's not the height versus time. Again, this, for the exact same reason before, makes no sense. This means most of the time there's actually two balls. The same ball is existing at two different places in the same time, right? Right there. The ball is in two different places at the exact same time. So that's the trajectory. But again, I'm asking for the height versus time. And so I'll start the same way. Goes up. Let's say right here, hits the backboard, but now it bounces back towards the player, so maybe it bounces something like this, and then, I don't know, I'll say it goes something like that, hits the ground, or maybe gets caught. But the key is, it is, again, always going, time is always going forwards. All right, so something like that would work. Now for all of these, and this is what may be kind of strange, is that there are definitely correct answers and wrong answers. It's not like whatever you draw is right. But what we're trying to pay attention to are not the details of exactly where is the height here, you know, how long does it take to hit the ground. In fact, all my graphs are just, what I'm interested in is the shape of the relation, not the actual, any values on it. And the shape is potentially not so easy to figure out. Okay, and it all depends on what we're comparing. For these examples, it was always height and time being compared. Time on the x-axis, height on the y-axis. But if I change the parameters of what I was looking at, then the graphs would all change. Okay, don't underestimate the importance of this, even though it maybe feels kind of different because we're not looking at any numbers actually in these questions, and we're not looking at any algebraic equations. This will kind of form the foundation for a lot that we'll do, not only in this course, but all future math courses. Okay, visualizing change on a graph. With that said, the homework, I'm going to stop writing it down here, but it is from the textbook, and so you'll see it on that sheet that I handed to everyone, or was on the Teams page. And so again, the homework for this is from chapter 5 in the textbook. And that's all. So thank you.